Welcome to WikiPodcast. Take a moment to imagine gazing up at the night sky. You see all those stars, galaxies, these huge stretches that look completely empty. It's quite something, isn't it? But what if I told you that everything you can see out there, every single star, galaxy, all the dust, makes up less than 5% of, well, everything. That a huge majority, like 95%, is totally hidden, silent, unseen. Today we're going on a really deep dive into the cosmos. We're exploring these invisible forces that are, shaping entire galaxies and actually accelerating the expansion of the universe. Dark matter and dark energy. We'll try to unpack what scientists think these invisible things are, why they're so sure they exist, and how looking for them is, frankly, rewriting our whole understanding of the universe.
It's a pretty staggering thought, really, and it completely changes our cosmic inventory. Our best model right now, what we call the lambda CDM model, gives us this surprising picture. Only about 5% is the ordinary matter we know. Atoms is stuff that makes up us, planets, stars. Then there's about 26.8% dark matter and a whopping 68.2% dark energy. What's really mind-blowing is that dark matter by itself is about 85% of all the mass in the universe. And together, the dark matter and dark energy, that's 95% of the total mass energy content. And yeah, dark matter is dark because it just doesn't seem to interact with light or any electromagnetic radiation, really. Its main thing seems to be gravity. And while it's like everywhere, its density right here in our solar system is actually much, much lower than regular matter.
Okay, let's unpack this. 95% invisible. It's hard to wrap your head around. How do we even start to think that most of the universe was, well, missing, hidden from us? It sounds almost like science fiction.
Well, the first sort of whispers of this actually go back further than you might think. Way back in 1884, Lord Kelvin was talking about dark bodies that might explain how stars were moving near the sun. There were others, too. Poincaré uses the term matière obscure, dark matter, in 1906. Kapteyn and Oort had ideas in the 20s and 30s based on star speeds, though Oort's measurement turned out to be off later. But things really started getting serious in 1933 with Fritz Zwicky.
Ah, Zwicky, right. And the Coma cluster. This is where it gets really interesting, isn't it? What did he actually find there?
So Zwicky was looking at this massive cluster of galaxies, the Coma cluster. Thousands of them. And he used something called the virial theorem to estimate its total mass. Think of it like if you see a swarm of bees buzzing really fast, you can kind of figure out how strong the hive's pull must be to keep them together, right?
Okay, so he's measuring how fast the galaxies are moving.
Exactly. Especially the ones way out on the edges. And he found they were moving incredibly fast. So fast that the gravity from all the stars we could see, it just wasn't nearly enough.
Not enough gravity to hold them in orbit? They should have just flown off.
Precisely. His calculations showed the cluster had something like 400 times more mass than what was visible. Now, his exact number was a bit off because the value for the Hubble constant was different then, but his main point was revolutionary.
That most of the mass holding it all together had to be dark, invisible.
Exactly. Most of the gravitational matter in that cluster was dark.
Wow. That's a huge claim for the 1930s. Was it immediately accepted?
Oh, not really. No, it was pretty radical, and honestly, it was largely ignored for decades.
Yeah.
It took until the 1970s for the idea to really gain traction, thanks mainly to Vera Rubin and her colleague Kent Ford.
Vera Rubin, right. She was looking at galaxy rotations. Andromeda, I think.
Yes, she was meticulously measuring how fast stars were orbiting within spiral galaxies, especially Andromeda, our big neighbor.
And what would you normally expect to see? And what did she actually find? Because this was another big shock, wasn't it?
Right. So based on gravity and where the light is, meaning where most of the stars and thus mass should be, you'd expect stars further out from the center to orbit slower, like planets in our solar system. Pluto goes way slower than Mercury.
Makes sense. Gravity gets weaker further out.
But that is absolutely not what she found. Rubin discovered that stars in the outer parts of these galaxies were moving just as fast, sometimes even faster, than stars closer in.
Faster? How is that possible?
It was as if each galaxy was embedded in this enormous invisible halo of mass. Something huge, extending far beyond the visible stars, providing extra gravitational pull.
An invisible halo.
Yeah. And this wasn't just her optical work. Radio astronomers looking at hydrogen gas, which you can detect way out beyond the stars, saw the same thing. By the end of the 70s, these flat galaxy rotation curves were undeniable. It forced the issue. Dark matter halos became, a major unsolved problem in astronomy.
Okay, so we've gone from these early hints and weird observations to really strong evidence just from how galaxies spin. But the case for dark matter and dark energy doesn't stop there, right? There's more.
Oh, much more.
Yeah.
The evidence now comes from all sorts of different angles, and it all points the same way. It's incredibly consistent. So yeah, we have the galaxy rotation curves. That flatness is a direct sign of unseen mass way out in the halos. Without it, galaxies would literally fly apart. Then there's velocity dispersions. In things like elliptical galaxies or globular clusters, big balls of stars, we see the same thing. The stars are moving faster than the visible mass can account for. Again, implies hitting mass.
So it's not just spiral galaxies, it's other types of systems too.
Exactly. And then you scale up to galaxy clusters. These are the biggest gravitationally bound things we know. We can measure their total mass in like 3 totally separate ways. One is looking at how fast the individual galaxies are moving within the cluster. Another is by measuring the X-rays coming from the superhot gas that fills the space between galaxies. And the third is gravitational lensing.
Gravitational lensing. That's Einstein's idea, right? Mass bending light.
Precisely. And the key thing is, all 3 methods, galaxy speeds, hot gas, and lensing, they all agree. They all tell us that dark matter outweighs the normal visible matter, stars, gas, by about 5 to 1 in these huge clusters.
5 to 1. Wow. And you mentioned lensing. Isn't there a famous example involving colliding clusters? The bullet cluster. People call it the smoking gun.
Ah, yes, the bullet cluster. It's a fantastic piece of evidence. It's basically the scene of a cosmic crash between 2 galaxy clusters. They've passed right through each other. Now, the ordinary matter, the hot gas clouds, interacted electromagnetically as they collided. They slammed into each other, slowed down, got shocked, and you can see this hot gas cloud sort of lagging behind in X-rays.
Okay, so the regular stuff got stuck in the middle.
Right. But the dark matter, because it doesn't really interact except through gravity, should have just sailed right through the collision without slowing down much.
It did it.
That's exactly what the gravitational lensing map shows. The lensing effect reveals where most of the mass is. And in the bullet cluster, the bulk of the mass, the dark matter, is located out ahead of the visible hot gas clouds. It's separated.
The mass and the light are in different places.
Exactly. It's incredibly hard to explain that if gravity itself is just behaving weirdly. But it makes perfect sense if dark matter is a real substance that doesn't interact electromagnetically. It's seen as pretty direct proof. And gravitational lensing in general is a powerful tool. Strong lensing can distort background galaxies into these amazing arcs and rings around massive clusters. Weak lensing causes much tinier, subtle distortions over large areas of the sky. But both depend only on the total mass present, not whether it shines or not. And consistently, lensing maps show way more mass than we can see, revealing the large-scale distribution of dark matter.
Okay, the evidence for dark matter seems really solid from gravity, but you mentioned dark energy earlier too. Where does that fit in? How did we figure that out?
Right, so dark energy comes from a different line of evidence, measuring the expansion of the universe itself. This involves type Ia supernovae. These are specific kinds of exploding stars that basically always explode with the same peak brightness. They act like standard candles.
Standard candles, like, you know how bright they should be so you can tell how far away they are based on how dim they appear?
Exactly. So in the late 1990s, 2 independent teams were using these supernovae to measure distances and map out the history of cosmic expansion. They expected to see the expansion slowing down due to gravity pulling everything back together.
That's not what they saw.
No. To everyone's shock, they found the expansion is accelerating, speeding up.
Speeding up, so something is actively pushing the universe apart, like anti-gravity.
Sort of, yeah. That's the idea behind dark energy. It's some kind of mysterious energy field or property of space itself that has this repulsive gravitational effect driving the accelerated expansion. And this ties back into the overall energy budget of the universe. Observations suggest the universe is spatially flat, meaning its total mass energy density is very close to a critical value. But ordinary matter and even dark matter together only account for about 30% of that critical density. The other 70%, that's attributed to dark energy. So the numbers sit roughly 5% ordinary matter, 27% dark matter, and 68% dark energy.
Wow. And does anything else back this up?
Absolutely. The cosmic microwave background, or CMB, this is the faint afterglow of the Big Bang, light from when the universe was just 380,000 years old. It's incredibly uniform, but it has tiny temperature fluctuations like little hot and cold spots. These patterns, especially the size and strength of these spots, the acoustic peaks, are extremely sensitive to the composition of the early universe. While ordinary matter interacted strongly with light back then, while dark matter didn't. This difference affected how those early density fluctuations could grow. Dark matter could start clumping earlier because it wasn't pushed around by the light pressure. By precisely measuring these patterns in the CMB with satellites like WMAP and Planck, scientists can basically read off the proportions of ordinary matter, and dark energy needed to create the sound spectrum we see. And the results strongly confirm the lambda CDM model with those same percentages.
It also helps explain how structures formed, right? Like galaxies and clusters.
Yes, structure formation is another key piece. There's a timing problem. In the early universe, the intense radiation would have smoothed out any small density fluctuations in ordinary matter. It would have prevented it from collapsing quickly enough to form the galaxies and clusters we see today.
So how did they form?
Dark matter provides the solution. Since it didn't interact with the radiation, clumps of dark matter could start growing very early on, creating gravitational wells.
Like a scaffold.
Exactly, a gravitational scaffolding. Then, once the universe cooled enough for ordinary matter to decouple from the radiation, it could fall into these pre-existing dark matter wells, eventually forming the galaxies and the cosmic web structure we observe. Without dark matter, structure formation happens too late and looks different. There's also evidence from baryon acoustic oscillations, BAOs, which are like frozen ripples in the distribution of galaxies left over from sound waves in the early universe plasma. They act as another standard ruler, and measurements of them also support the lambda CDM model.
Okay, it's genuinely an overwhelming amount of evidence from so many different areas: galaxy rotation, clusters, lensing, supernovae, the CMB, structure formation. It all points to this invisible universe. So the million-dollar question, or maybe trillion-dollar question, what is this stuff? What could dark matter actually be made of?
That is indeed the huge question driving a lot of particle physics and cosmology research today. First off, we're pretty sure most of it is not baryonic matter. It's not made of the protons and neutrons that make up us and everything we see.
Why not? Couldn't it just be like loads of black holes or dim stars or planets floating around, stuff we call machos?
Well, there are several strong arguments against that. One, if it was just normal matter hiding, like vast clouds of gas or dust, we'd expect to see its effects like absorbing or scattering background light, and we don't, not nearly enough. Two, and this is a big one, Big Bang nucleosynthesis. This theory very accurately predicts the amounts of light elements, like hydrogen, helium, and lithium, created in the first few minutes after the Big Bang. These predictions only work if the total amount of ordinary baryonic matter is around 4 or 5% of the universe's critical density. But we know from gravity that the total matter density is closer to 30%. So most of that matter can't be baryonic.
Okay, so the math from the early universe just doesn't allow for that much normal matter.
Exactly. And also, direct searches for machos using microlensing, looking for stars temporarily brightening as a massive object passes in front, have been done. While they found some objects, they conclusively showed that machos can't make up the bulk of the dark matter in our galaxy's halo. Plus, the details in the CMB anisotropies also tell us that only about 1/6 of the total matter interacts with photons the way ordinary matter does. So most matter has to be something else.
So if it's not normal matter, it must be something new, something exotic, non-baryonic.
That's the leading conclusion. It has to be made of particles not currently in our standard model of particle physics. And the prime suspect for a long time has been WIMPs.
WIMPs, weakly interacting massive particles.
Right. These are hypothetical particles that would be massive, maybe tens to hundreds of times the mass of a proton, and would interact only through gravity and the weak nuclear force, hence weakly interacting. There was this idea called the WIMP miracle. Basically, theories beyond the standard model, like supersymmetry, naturally predicted particles with about the right properties, the right mass and interaction strength, that if they were created in the hot early universe, they would naturally end up with the abundance needed to be dark matter today. It seemed almost too good to be true.
A miracle. So how do you actually look for these WIMPs if they barely interact? Seems tough.
It's incredibly difficult. There are 3 main strategies. Direct detection experiments build ultra-sensitive detectors, often deep underground to shield from cosmic rays, filled with materials like liquid xenon or germanium. They wait, hoping a WIMP passing through Earth will occasionally bump into an atomic nucleus in the detector, causing a tiny detectable recoil. Experiments like LZ, Xenon, CREST are doing this.
Any luck so far?
There have been some potential hints, like the Demalopra experiment claiming an annual modulation signal, more events at one time of year as Earth moves through the galaxy's dark matter halo. But other, more sensitive experiments haven't confirmed it. So no definitive detection yet. The second approach is indirect detection. If WIMPs are their own antiparticles, they could annihilate when they collide in areas where dark matter is very dense, like the center of our galaxy or dwarf galaxies. This annihilation could produce detectable particles like gamma rays, neutrinos, or antimatter, positrons, antiprotons. Telescopes like Fermi and detectors like AMS on the space station are looking for these signals. There have been some intriguing excesses observed, but it's hard to be sure they aren't from normal astrophysical sources. And the third way is collider searches. At places like the Large Hadron Collider, LHC, they smash particles together at incredibly high energies, hoping to actually produce WIMPs or other dark matter particles. Since the WIMPs wouldn't interact with a detector, they'd escape unseen, carrying away energy and momentum. So physicists look for collisions where there seems to be energy missing. Again, no confirmed discoveries yet.
So WIMPs are still a possibility, but the lack of detection has people looking elsewhere too.
Exactly. As the WIMP searches have come up empty so far, other candidates have gained more attention. One very interesting possibility is axions. Axions are another type of hypothetical particle originally proposed to solve a completely different problem in particle physics related to the strong nuclear force. They would be incredibly lightweight, much lighter than electrons, and interact extremely weakly.
Lighter, not heavier like WIMPs.
Yeah, potentially ultralight.
Yeah.
Because they're so light, they'd behave more like a quantum wave on large scales, which might actually help resolve some minor discrepancies between the standard dark matter model, lambda CDM, and observations on small galactic scales. There are experiments like ADMX specifically designed to hunt for axions. And then there's another, perhaps more conventional idea, but still non-baryonic, primordial black holes, or PBHs.
Black holes formed right after the Big Bang, not from stars.
Correct. These wouldn't be made from collapsed stars, so they wouldn't count as baryonic matter according to the Big Bang nucleosynthesis limits. They could have formed from the direct collapse of very dense regions in the extremely early universe. The cool thing is they use known physics, general relativity black holes, and there was a surge of interest when LIGO started detecting mergers of black holes around 30 times the mass of the Sun, a range that's a bit tricky to explain with standard star evolution. Could some of those be PBHs?
Is that plausible? Could they be all the dark matter?
Probably not all of it. Various observations, like gravitational microlensing searches, which would see PBHs if they were common, and searches for the Hawking radiation they'd emit, especially if they were small, have put pretty strong limits on how many PBHs could be out there, especially in certain mass ranges. But they could still potentially make up some fraction of dark matter or exist in mass windows we haven't fully probed yet.
So WIMPs, axions, primordial black holes, lots of candidates. But what about the idea that maybe we don't need any of this stuff, that maybe our understanding of gravity itself is wrong on these large scales?
That's the modified gravity approach. A minority of physicists explore this. The most famous is MOND, modified Newtonian dynamics. It suggests that gravity might behave differently at very low accelerations, like those experienced by stars in the outer parts of galaxies. And MOD can actually explain galaxy rotation curves quite well without needing dark matter halos.
So why isn't it the mainstream view?
The big challenge for MOND and other modified gravity theories is explaining everything else. While they might work for galaxy rotation, they typically struggle significantly with explaining the observations of galaxy clusters, especially the bullet cluster, where mass and light are separated. They also have trouble fitting the precise pattern of the cosmic microwave background anisotropies and explaining large-scale structure formation in the same way dark matter does. Basically, no modified gravity theory has yet been able to successfully explain the entire range of observations that dark matter accounts for. That's why most astrophysicists think that while gravity might be more complex than we realize, some form of actual dark matter particle is still necessary.
It really is incredible, so much evidence pointing towards it, yet it remains so hidden. Which brings up a question. If dark matter is everywhere and makes up so much of the universe's mass, why can't we see it directly? And maybe more fundamentally, why doesn't it seem to clump up and form things like planets or stars made of dark matter? Why is it just these diffuse halos?
That gets to the heart of why dark matter is so different from the matter we know. There are two main reasons it stays diffuse and invisible. First, it can't cool down efficiently. Think about how a star forms. A gas cloud collapses under gravity. It heats up, but atoms and molecules in the cloud can radiate that heat away as light. This cooling allows the cloud to keep collapsing down into a dense star.
So shedding energy is key to clumping up.
Absolutely. Dark matter particles, however, don't interact electromagnetically, so they can't easily radiate energy away as light. If a cloud of dark matter starts to collapse and heats up due to compression, it doesn't have an efficient way to get rid of that energy. The particles just speed up and resist further collapse. They can't cool and condense into dense objects.
Okay, so no way to lose heat means no way to form dense things. What's the second reason?
It's the lack of diverse interactions. Ordinary matter is complex because particles interact via the strong force, binding nuclei, the electromagnetic force, making atoms and molecules generating light, and the weak force, involved in some nuclear reactions in addition to gravity. These interactions allow for chemistry, nuclear fusion, building complex structures like planets and life. Dark matter seems to interact significantly only through gravity and possibly the weak force if it's a WIMP, but not the strong or electromagnetic forces. Without those richer interactions, it just can't build complexity. It can clump gravitationally into halos, but it can't form atoms, bind together chemically, or undergo fusion like ordinary matter. It just stays as this relatively smooth, diffuse component.
So it's fundamentally simpler in a way, just responding to gravity on the large scale.
In a sense, yes. Its simplicity is part of its mystery and why it behaves so differently. And, this raises a really profound question. If dark matter is so fundamentally different, so unlike everything we experience directly, interacting almost purely through gravity, what other, perhaps even stranger, unseen aspects of the universe might we still be completely oblivious to? What other fundamental secrets are out there, hidden in plain sight?
That's a fascinating thought to leave us with. The search continues. Thanks for listening. Write us your opinion on what you think the greatest challenge in discovering the true nature of dark matter will be in the comments. Subscribe to the channel to help more listeners reach our deep dives. Thank you and have an amazing day.